Welcome everyone to another CITA seminar. So today we're very lucky to have Mark Gieles join us from ICUB in Barcelona. So Mark got his PhD from Utrecht in the Netherlands. He then went on to be a VLT support astronomer and ESO research fellow in Chile. After which he became a Royal Society University Research Fellow at Cambridge, a very prestigious thing in the UK. After which then he became one of the founding members of the astrophysics group at the University of Surrey. And now he finds himself as a professor in Barcelona, where he is an expert on all things black holes in globular clusters and just general globular cluster physics as well. So yeah, it's really nice to see you, Mark, and take it away when you're ready.
All right, thank you very much, Ted, and thank you everybody for joining us, and for the people making time earlier today to chat about their work. It's been this visit has been very pleasant, although virtual. With two small children, actually, it's for me quite convenient to have these virtual visits nowadays. So today I want to talk about this general topic of what we know about black holes in globular clusters, and if they're there, why we care about that. There will be a particular cluster I like to focus on towards the end, which is Palomar 5, which I show here on the front slide. And it's not such an impressive globular cluster. It's actually looks more like an open cluster that we find in the disk of the Milky Way. It's rather transparent. And but I hope today to convince you that it might be these rather boring looking globular clusters that are worthwhile investigating in a bit more detail. So this work done with several people over the last few years, some from Surrey, some have moved on and some are still there. And right, so let me start with giving a bit of a motivation of why we want to do this. Let's see if I can actually change the slide here. That seems to be not working. There we go. So the overarching goal is to understand how the gravitational wave source, and in particular the binary black holes that have been found with LIGO and Virgo in the last 5 years or so, how they form. So here you see an overview of the latest gravitational wave transit catalog of nearly 50 or over 50 sources, their progenitor masses and their merged masses. And you can see they span an enormous range from roughly 5 or 10 to all the way up to above 100 solar masses, which is well above the typical X-ray binary masses we have inferred from Milky Way black holes. And the question is, how do these systems form, right? We know that general relativity will make them spiral in over Hubble time if they start with typical separations of less than an AU and or either high eccentricity. But that configuration is basically the question. How do these binaries form in these type of configurations? And if you want to really take a step back, we can ask even the question: are these black holes primordial of nature? Are they part of the dark matter in the universe, or are they astrophysical of nature? Are they the end results of massive stars? Now, if you choose to assume that these black holes all have an astrophysical nature, there are still various channels that can produce the mergers. Now, they roughly fall in two camps, and there are actually a lot of variations and totally different channels that touch on these, but should maybe be included. But just for the point of this talk, I'll simplify it to two avenues. One is where two massive stars form in a very tight configuration initially, such that near the end of the main sequence of one of them, a contact phase or a Rush-Lobe overflow phase ignites that brings the stars closer together, and even a common envelope phase is required in most models, and leaves behind two black holes very close to each other. And in the second model, these two black holes are initially not gravitationally bound, but they sit in a star cluster which is very dense. And then they sink to the center by gravitational friction, so the slowing down because of slingshot against lower mass stars. And it's been shown that the density and the dispersion in these globular clusters are such that the probability of making very tightly bound binaries is high enough that they might produce these binaries as well. And these different models, they make different predictions, as you can imagine. Since the discovery of gravitational waves, there's been an explosion of work on making predictions for what to expect. So they make predictions for the redshift zero rates, but also the rates as a function of redshift, the mass ratio of the binaries, the spin distribution, the individual spin, but also the dimensionless spin, which is a projection of the spin on the orbital plane. I think it's fair to say that as of now, both channels are very good at explaining all the observables. So we have two winners. I mean, the picture here is of the two high jumpers from the Olympic Games who shared the gold medal. So if one is isolated and the other one is dynamical, so far we both have successful models that can explain the data. But of course, this is a very unsatisfying situation to be in, because they can either be one right or you're only half right, and then both need to change something in their models. So one particular observable I've been interested in recently is the eccentricity, because that seems to be something that can only be produced in the dynamical channel. And hereby I mean an eccentricity at the frequency of the gravitational wave interferometers. So at 10 to 100 hertz, it's been shown by various people that you can make such eccentric binaries that still have a remnant eccentricity distribution. That if you look here at the result of one particular globular cluster for the cumulative eccentricity distribution at the time of merger, there's about 5% of the mergers that have an eccentricity above 0.05. And that's in principle, we can measure this in the next observing runs. And there have been 2 cases already where eccentricity has been detected for that. Now, I want to not talk too much about the gravitational wave part of this, but more about the model to make them. So very briefly, a very schematically shown here is the process of binary formation in the moment of highest density in a star cluster. So every star cluster, because of the two-body relaxation processes that go on inside of them, the interactions between stars, they tend to transfer energy from the core to the center, and this process makes the density in the core higher until you form a binary star typically. Now, in a cluster where all the stars have the same mass, this can take several relaxation times, and for the clusters we know of, that this means several giga years. But the black holes can do this much faster, so they can do this on a very small fraction of the relaxation time of the cluster, which can be tens or hundreds of millions of years. And once these black holes reach the center, you can see that there's an attempt of making a bound member. So meaning a bound binary, where 2 stars are leaving a 3 or a 4 body interaction in a bound configuration. Now this happens all over the lifetime of a star cluster. So these globular clusters we know of in the Milky Way, they formed very soon, within a gigayear or so after the Big Bang. And in the first couple of hundreds of millions of years or a gigayear, these black holes, they sink to the center. They form binaries. These binaries, they start interacting with the individual black holes. They can be ejected. The binaries themselves can get ejected as well in recoils in interactions with single black holes. And then there's various avenues towards mergers. They can either merge inside of the cluster, or some of these ejected binaries can also merge outside of the cluster. And this is gives us an exciting opportunity to look back in time and study the properties of globular clusters with their gravitational wave sources. But at the same time, it makes it very challenging to make predictions for this model, because it depends on properties of the cluster that are long gone. So we need to really understand how dense and how massive these clusters were soon after formation. Now, we've gone a long way. There's a lot of groups working on this. I'm showing here one example of a forward modeling technique that Fabio Antonini and myself have been working on in the last few years, where we show for different initial assumptions of the density of the star clusters, the merger rate of binaries as a function of the mass of the primary. So as a reference, I show here the initial mass function that our stellar evolution model provides. And you can see that the mergers are biased towards the more massive clusters. They tend to sink to the center first and merge first. And depending on the initial density of the cluster, we can sort of match or fit almost the observed merger rate and read off the initial density. And we can also see that in the extreme parts of the mass function of the mergers, we cannot reproduce the data. So this is an interesting constraint and allows us and also the isolated binary community to think further on how the lower mass and the more massive objects can be made. Now, in these models, we need to make assumptions about how globular clusters form. So this involves the mass function of the clusters themselves, their densities, at what rate or as a function of redshift they form, the metallicity distribution, the stellar IMF within them, and then the initial final mass relation of the black holes, the nasal kick. So there's a lot of uncertainties in these models. But then when we forward evolve this in time, in principle, this is a trivial exercise. It's numerically challenging and it's computationally challenging, but we do understand the Newtonian dynamics that takes place inside of these globular clusters. So we should be able to forward model these initial parameters into the present day properties of both the globular clusters, but also the binary black holes that they produce. So the general idea of what we're trying to do is to use the observed properties of globular clusters to constrain the model and the initial conditions in specifically. And perhaps in the future, we can then use also the gravitational waves themselves to further provide constraints on the initial conditions of how globular clusters form. So we're far from that, so don't get your hopes up too much. I'm going to talk about the first steps. So before I move into this, perhaps maybe this is a natural moment for a short pause and maybe a question, if that's applicable.
Quick question. If you have two viable channels, then how do you set constraints on globular clusters without also setting constraints on the other channel?
Yes, it's an excellent question. Yeah, so the ideal scenario would be where we are able to fully reproduce all the observed properties of the globular clusters, and then you would be able to subtract whatever the globular clusters do from the observations, and any sort of difference in what the isolated binary channel then would say about the remaining gravitational waves is either something which is wrong in our prediction or in theirs, right? So it's not trivial. But let me leave it at that. It's difficult, and we need to collaborate strongly with what the other models predict there as well. That's much easier said than done. Right, so for the second part, I'd like to move on to what we actually know about black holes and globular clusters. And let me start by how the search for these stellar black holes started. And this was in globular clusters, mainly driven by the search for the so-called intermediate mass black holes that sit in between the sort of 10 to 30 solar mass stellar black holes and the supermassive black holes in the galaxy centers. And from the well-known M sigma relation, which relates the mass of the black hole in galaxies to the velocity dispersion of the hosts, or of their bulge, to be more specific. If you would extrapolate this to the masses of intermediate mass black holes of around 10 to the 3 or 10 to the 4, you are at the velocity dispersions of globular clusters. And this is why people started looking for these somewhat more massive objects in globulus. And there's been a lot of work done claiming or finding intermediate mass black holes in various globular clusters. This is an incomplete list, but for every claim or every paper, there exists at least one counter argument where either they show that there's something wrong with the observations, or there's something wrong with the model, or a combination of these two. So there's no hard evidence at the moment for the existence of intermediate mass black holes. Now, it's not yet evidence for their absence. They are very difficult to find, especially if you want to rely on dynamics. The sphere of influence is very small, so only a few stars that are seriously affected by the gravitational potential. And this led the group of J. Strader to look for radio continuum with VLA and some nearby globular clusters, well, in total, nearly 50. With the idea that even if there's no accretion disk or there's no binary companion, there would still be red giants nearby with winds, and these winds would interact with the intermediate mass black hole. So you could expect at least some very weak radio continuum from nearby globular clusters. And they found that there is no such signal, and they put limit on IMBHs in these clusters of maximally 1,000 solar mass. So if there are any, they should be below that. But they did find in several globulus, in 3 or 4, they find radio. Sorry.
Mark, I just wanted to interrupt. This is Norm Murray.
Oh, hi.
Hi, how you doing?
Yes,
Haven't seen
very
you for
well.
a
Nice
while.
to see you again.
So I had a question about the radio searches. I mean, you referred to
Yes.
winds from red giant stars, but I immediately started thinking about there are really tight constraints on the dispersion measure in globular clusters, incredibly tight ones, right? And,
Yes.
I mean, maybe from the millisecond pulsars that are blowing the gas out or whatever. So in those searches, what were they actually using for the density of the interstellar medium or whatever you want to call it in the globular? Did they do some model from saying there's some wind from a red giant, or did they actually use the really tight constraints on from the dispersion measure?
To be honest, I don't know. I don't know.
Okay, all right, it might be worth.
It's a
I'll
good
go
point.
back and look.
Yes,
Yeah.
I'll look into these papers to see if this it's a good point. If they're very low, right? There's a very little
Yeah,
gas
it's
in
ridiculously low. Yeah.
Yeah,
It's crazy.
yeah. It's almost difficult to explain why there's so little gas.
Exactly, it is difficult to explain. Yeah, exactly.
Yeah, yeah,
Okay,
yeah.
thanks.
Yeah, no, I apologize. I don't know too much. So they found several accreting objects here, which were bright in radio and weak in X-ray, which points at a low mass, at least lower than intermediate mass black holes. They couldn't precisely infer the mass from this, but they're most likely stellar mass black holes with either a dwarf companion filling the rush lobe or an accreting white dwarf. And at roughly the same time, there's been some insight in our like theoretical understanding of populations of black holes and globular clusters. So for several decades, there's been this meme where there's this thing called the Spitzer instability, where black holes, if they're too massive, or the population of black holes is too massive, you can show with very simple equipartition arguments that the population of black holes is unable to achieve energy equipartition. So they start sinking to the center in an attempt to achieve this equipartition. But before they reach it, so they're still moving too fast for equipartition, the subcluster of black holes becomes self-gravitating, and Spitzer actually very safely doesn't really say what would happen, but most people then interpret that as, well, this would be such a short time scale evolution that this small subcluster will have, because it's very dense with relatively few particles. So the corresponding dynamical time scale, the relaxation time, is very short, and we expect this cluster to basically eject itself from the cluster very quickly early on in the evolution. But at around the time that Jay Strader was finding his VLA objects, a PhD student of Douglas Hagee showed that, in fact, that's not what happens. The subcluster does shrink to a very small size, but it then starts essentially acting like an isolated star cluster, which will expand initially much more than it will eject stars. So while it expands, it finds a sort of thermal contact with the stars around them, and it stops its expansion. And it sits in a sort of equilibrium configuration that can last very long, at least for many relaxation time of the clusters, which can mean about a Hubble time for most globular clusters in the Milky Way. So if they are remained or retained after the natal kicks, they can still be there. Now and then the Muse GTO team, so people had a lot of time on the integral field unit on the VLT observatory. They observed a couple of globular clusters with a lot of different epochs, looking for radio velocity variable stars, and they found a few very extreme objects in this cluster in particular, with radio velocity variations of 150 kilometers per second. And then folding them in the same phase, they inferred a companion mass that is above 4 solar masses. So these are very strong black hole candidates around these stars in this globular cluster. And then recently, the group in Liverpool, they showed in a much younger star cluster in the LMC that there is a very strong radio velocity variation as well, including a photometric variability, which pointed at a black hole of around 11 solar masses. But it took Karim El-Badri about 48 hours to come up with an alternative explanation for this object. So for the interested reader, you can look at the model of El-Badri, which is suggesting this is actually a stripped star, which is much lower mass than the turn-off mass. And perhaps the companion isn't as massive as 11 solar masses. But I think this is not the last we'll hear about this particular object. Now, that brings me to what do we actually expect? for how many black holes there are, because finding a few binaries might actually imply that there's a whole population, because a star with a black hole companion is probably the least likely configuration for a black hole to be in. Right? If a black hole sits in the center and it forms a binary, it's most likely with another black hole. So several people have suggested they might be the tip of the iceberg. And one can get some handle on how many black holes to expect by doing a simple exercise, by starting with a canonical initial mass function for some stellar mass function, for some stellar mass comparable to a globular cluster, the metallicity comparable to the globular cluster peak. And then you evolve it with a stellar evolution model. I used Jared Hurley's fast SSE. And the final result depends sensitively on the wind prescription and the natal kick scheme. Here I used the implementation by Samaran Banerjee, which is based on the Fryer and Belczynski models, where a large fraction of the black holes do not receive a kick because of fallback. And then at the age of 12 gig years, you see that about 6.5% of the black holes of the total mass of the globular would be in black holes that has not been kicked. So they would still be there if there wasn't any dynamical interaction. And then a few more percent of black holes would have received a kick. And whether they're still there depends on the escape velocity at birth, the same for the neutron stars. So it's actually quite a substantial fraction of the present day mass. So in a schematic diagram, not linear, not log, but something in between, if you would like to know the frequency of the mass fraction in black holes of globular clusters, we will have to start with a range between 5 and 8%, depending on metallicity and velocity kicks. And then we can wonder, well, is that actually what we observe? And I first want to place a word of caution, because this few percent, although it seems very minor, it's actually quite close to the inferred mass fraction of intermediate or supermassive black holes in ultra-compact dwarf galaxies and in a few globular clusters. So here I show a plot by Karina Vogel and Anil Seth, who looked at some of the UCDs that have reported black holes in them and some of the globular clusters. And the inferred mass fraction are somewhere between 1 and 10%. And that's actually quite similar to the expected stellar black hole mass fraction. So I've had many entertaining discussions with people working on these UCDs about whether they should be worried about this or not. So the most extreme and the case where several groups have worked on is Omega Centauri, which actually was a candidate to have an intermediate mass black hole. But several groups have now shown that there is evidence for a dark mass, and it's centrally concentrated. And it's more centrally concentrated than what the white dwarfs can achieve. You can, with some models that have some prescriptions for the degree of equipartition in them, you can show this. And Aditya Chokhi showed that the velocity dispersion as a function of radius for omega Cen is elevated when compared to an isotropic model that describes the light distribution, so the surface brightness profile. And even if you would try to get an anisotropic model that cannot reach the center, you really need to add some dark mass in the center to explain the velocity dispersion. And she found that around 5% of the total mass is expected to be in black holes, and she could even get some handle on the masses of these black holes. And then just a little bit later, Holger Baumgart showed with a suite of embody models that he compared also to omega Cen, that if you look at the line of sight velocity distribution, you would expect, in the case of an intermediate mass black hole, quite a long tail going all the way up to 80 kilometers per second, where the data shows that it's truncated at around 60, and in nice agreement with his models, where he also has about 5% of the mass in stellar black holes. So I really like this because it adds a lot of information to the velocity dispersion, because to some degree the dispersion profiles are degenerate with the intermediate mass black hole models. Now then there's this peculiar cluster NGC 6101, where D'Alessandro showed that if you make the cumulative profile radial distributions of stars of different masses, they look all very similar, despite the fact that you expect there to be some mass segregation with the more massive blue stragglers, for example, to be more centrally concentrated, but it's not the case. And then I had a PhD student who looked at this So here you see the data, and here you see the same cumulative distributions for different tracers with different masses for models where we retain different fractions of the black holes. So we confirm indeed that if you wouldn't have any black holes, you should see a difference between the neutron stars and the turn-off stars, for example. Whereas if you add some black holes, the segregation among the stars and the neutron stars really shrinks and to almost unobservable amount. And here we concluded that about 1 or 2% of the total mass is in black holes. Now, Vincent pushed this a little bit further in 47 TAC. So I showed the image here because you can almost see by eye that the inferred black hole fraction somewhat anti-correlates with the central density of the black hole. So he used multi-mass models again to explain the surface brightness and the kinematics, the dispersion, but also the mass function at different distances from the center, which these models can do. And he left the black hole population as a free parameter. And it seems a little bit hard to believe that you can infer 0.05% fraction of the mass, but because they sit in the center, that actually this fraction is much higher in the place where they are, and also this is where the best velocity data are. So the models are in fact somewhat sensitive to what if you put less than the percent of the mass in black holes. And I wouldn't make a strong claim here that they're black holes, but at least the posteriors show that it's allowed, and there's a clear limit that cannot be much more than 1,500 solar masses. And this result is in agreement with completely different methods of people who try to model the evolution of the cluster and then explain the observations with so-called Monte Carlo models. And the answers are far apart by an order of magnitude, but they both show that some black holes are required, otherwise the core would have already collapsed. Now, various groups have done this for with looking at the structural properties for a whole suite of clusters, about 40 or so. And although the individual clusters, these are just their NGC numbers, the individual groups, they tend to find different answers. It's because they use different methods as well. But you can see at least both of them, they find a range of between no globular clusters or no black holes at all to a few thousand solar masses in black holes. And if I add the dynamical models that we've been comparing to some of them in common, we tend to roughly agree. So at least for this one, this particular case, this is a core collapsed cluster. So here we find there's absolutely no space for any black holes. 47 TAC, it's a small amount. And then omega sen is off the chart because it's almost 100,000 solar masses. And the spread in here, we don't think it's because of differences in retention fraction or peak velocities. It's most likely due to dynamical ejections. So clusters like NGC 6624, the core collapsed cluster, probably has just ejected all its black holes and is now going into a core collapse with the stars. So the stellar density is going up. And so that means that we can expect anywhere between 0 and the initial fraction after supernova kicks. Now, this has led to a somewhat new interpretation of a phenomena called core collapse in globular clusters. If you look at the surface brightness profile as a function of radius of globular clusters in the Milky Way, you can roughly divide them in two groups: the ones that have a flat, large core in the center, and it's called a king model-like decline, and the ones that have a parallel profile that is very cuspy down to the resolution limit of the imaging. And so the left ones are called pre-collapse, so clusters that are on the way to core collapse, as I showed in the video in the beginning. And the right ones are interpreted as the ones that have achieved core collapse. But Breen and Haggy put a little twist here in this interpretation and said, actually, these pre-collapse clusters, they might very well be post-collapse from a dynamical point of view, but it's the black holes that are creating binaries, and therefore they puff up the core. Whereas the ones that we call core collapse, they have just ejected all their black holes. And so they now have a collapse in the stellar profile and are making stellar binaries, or more likely white dwarf and neutron stars. Now, if this is correct, it means that about 80% of the globular clusters still has a substantial fraction of its mass in black holes. Maybe here's also a good moment for a brief pause if there are any questions. Otherwise, I'll just take a seat.
There was a paper on arXiv, I think just today, arguing for the presence of an intermediate mass black hole in the brightest M31 globular cluster. Have you had a chance to look at that, and have you any comment on how believable that is?
Yes, I'm very well aware of that paper. I had many discussions with Anil about that paper. This is the case where I place a word of caution, because the total mass of the black hole implies that it's 1% of the total mass of the whole system. And I do believe they can measure that, but I believe they also try to show, and I encourage them actually to see if they could see if the mass is resolved, right? Because it's M31, so it's much closer than the UCDs, and it is and it is not resolved, because there are models now that tell us basically how extended the stellar black hole population should be, and that is very close to their resolution limit. And it turns out that if they play with their inclination a little bit, it is just barely resolved or just not. So it's very, I would say it's very difficult to say with certainty that is one or the other, right? So I don't believe that there must be some of these black holes, right? So it could very well be, but I don't think it's ruled out that they're not stellar black holes. Let me put it that way. Or it's a combination of both, and that's actually the more interesting outcome, that there is an IMBH and the stellar black hole population around it, and dynamically that would make for a very new problem, because that's much harder to model, and I don't think they're decent models to make predictions for that. Right, so the third part and final part, I want to show some results on stellar streams, which, yep.
There's another question in the room. I'll just pass you over.
Oh, sorry.
Hi, this is Chris Thompson. We go on to another subject.
Oh, I don't hear anything anymore.
You might have to step closer.
I don't hear anything, Ted.
Can you hear now?
Can you hear me now?
I hear, yeah, I hear you, Ted, but the other Chris was following.
Keep talking. Okay. Can you hear this?
Yes. Yes.
Hi. So the quick question is, so we do expect the progenitors of these black holes to have formed mostly in binaries. And how much variance is there in the results of the embody models of black holes in star clusters when you take into account the possible range of, binary properties that might have been present when those stars formed? Because in these environments, I guess we don't really know what the binary properties would have been, and there's always going to be some significant uncertainty in that.
Yes. Yeah, that's an excellent point. There was a very nice study actually last week by Long Wang on this, where he ran a suite of embody models with a new code, where he varied the initial binary properties to see how it affects the cluster evolution, but also the resulting merger rates. And what you assume for the high mass binaries is important. What you assume for the lower mass binaries doesn't seem to matter so much for the star cluster, but you find differences if you change vary the fraction from let's say 30 to 100%. Now, what actually happens on the level of mergers is a really good question. I don't think we know yet. And actually, I just started thinking about this a bit with Fabio Antonini and one of his students, that indeed almost all the binary black holes, or all the black holes, they also start in binaries most likely, which means that we shouldn't really worry too much about single binary interactions, but about binary interactions. And the outcome of those is could be much harder to predict, at least, than single binary. So there's a lot to be done there. I think it could make important differences. Yeah. for the cluster, I usually take this view that the cluster will evolve in the way it evolves, and the binaries are sort of an energy source for its relaxation process. So, and it's been shown that varying the binaries doesn't really affect the evolution of the bulk properties like the half mass size and the total mass. But what happens in the core could be altered quite substantially by the type of binaries you put in and how many. So. Okay, so in the last part, I want to say a few things about streams, and this work started with a postdoc in Surrey, Thomas de Boer, and Dennis Erkel, a colleague of mine, and they measured the photometric mass of all the stars in this stellar stream in the Northern Hemisphere, and because it's a very narrow stream, everybody was always assuming that this must have been a star cluster. So they asked me, well, can you run an embody model and get the mass from, or get the stream properties, and then we can compare it to the data. And then I found that, yeah, if you want to dissolve a star cluster on that orbit of GD1, which is very well constrained from proper motions and distances, then you cannot really get rid of a star cluster more massive than about 4,000 solar masses. So we're off by a factor of 3 or 4. And so I started wondering, like, how can this stream be so massive? And how did the stars get out of the star cluster? This I don't understand this. But because there's no star cluster found, it's very difficult to constrain any model with the observations, because we just see the stream. So there's a lot of freedom in what we can change in the initial conditions. So that's why we thought, let's first look at Palomar 5, which is seen here in the bottom. Similarly impressive stream, but it still has a star cluster associated with it. So in that case, I call it a sort of Rosetta Stone for understanding progenitorless streams. If we can come up with a model that can explain both the star cluster and the stream, well, then perhaps that lends some more value to the interpretation. So, and the star cluster is also really strange if you compare it to the rest of the star cluster population. So the average density within Palomar 5 is extremely low. It's actually comparable to the stellar density in the solar neighborhood. And because the orbit of Pal 5 brings it actually to about 9 kiloparsecs in pericenter, it means that every time it crosses the disk, the tidal forces are enormous, and the cluster is very close to complete dissolution. So here you see the orbit. It's currently close or just beyond apocenter and falling back through a pericenter around the solar radius. And so it's a very fragile cluster at the moment, and it is perhaps the reason why there are such prominent tidal tails. Now, but it doesn't really answer, like, how did it get so fluffy? And one attempt to explain this system was by Walter Daenen, who ran his Conditionless code, so a gravity solver where the two-body interactions are done with softening, and they're not really important. And he showed that if you start with relatively large initial conditions and a very high mass, you can actually create the prominent tails and end up with a very large cluster. So to some extent, this is what you put in is what you get out. But one of the problems I had a bit with this interpretation is that the model, the final properties are very sensitive to the initial conditions. If you change the size a little bit, or you change the central concentration of the model a little bit, the results could be changing by much more. So there's some fine tuning involved. Plus, the observed properties of Pal 5, they have some features very similar to all the other globular clusters. So the mass function is flattened, which points at mass segregation and the preferential loss of low mass stars. And there's a spread in the sodium abundance, which is the peculiar multiple population problems of globular clusters, something that's not seen in field stars. And we don't really know what this sodium spread is due to, but any model that is out there, and there's a large variety of models trying to explain this with either AGB stars, fast rotating massive stars, or even supermassive stars. In all of these models, the clusters start very dense. So if you adopt very fluffy initial conditions, you need to sort of rhyme that with the fact that many of the other properties of the cluster are very similar to other globular clusters. So I started trying to do this with a collisional embody code from Sverre Arset, where the two-body encounters are done in detail. So these codes are much more computationally expensive to run, but we can then study internal relaxation effects. And here this plot is just to show what the problem is if you sort of do this with your vanilla initial conditions. So I show here the mass loss rate and the absolute mass loss rate. Here, this horizontal bar is what the Daenen models required to get the tidal tail, so about 10 solar masses per million years. And this is what the embody, the sort of vanilla embody models in literature tell us, the Baumgart and Makino study, where they ran a large suite of embody models at different eccentric radii. So if you scale that to the orbit of Pal 5, you find something like this. So here I ran a few models with similar initial conditions. So initially a very high mass loss rate. This is by stellar mass loss, so it's not escapers. And then you have this even slowing down escape rate, which is about an order of magnitude below what you need to explain the tails of Pal 5. And then if you look at the same time at the size, the half mass radius or the half light radius starts evolving after an initial expansion. It starts evolving after a line of constant density, which is essentially the cluster filling its rush radius. And it no longer expands, and it starts actually losing mass and shrinking at a roughly constant density. And here sits Pal 5, so roughly 10,000 solar masses and a radius of 20 parsecs. So it's not a little bit off, it's substantially off, and it's very difficult to understand what's going on here if you rely on these kind of initial conditions. So here's what we did. So we set out with a suite of embody models with RSET's embody 6 plus actually, so a parallelized version for graphics cards and multi-core machines. So, and then we try to reproduce the large radius of the cluster and the tidal tails. So the initial conditions of the model are somewhat standard. So Plummer spheres with isotropic velocity distribution, Krupa IMF, stellar evolution for single stars and binary stars, but we didn't include primordial binaries. Then we use a Milky Way potential very close to Joe Bovey's 2014 model. And we vary then the initial mass of the cluster and its density, and we ran it with Sverre Arset's embody 6++. And Longwang's ++ edition, I should say. And we try to observe the embody models really in the observer space, so in RA and DEC and G magnitudes as the data. And then we made two very extreme assumptions about the black hole. So I didn't start completely uninformed about this, but it's been shown that if you leave black holes in, mass loss rate of clusters can go up and the expansion is higher. So we made two extreme assumptions. Either we left a large fraction in by using these fallback and momentum conservation assumptions from the Fryer models, or we gave them the same kicks as neutron stars, and then essentially we lose all the black holes. So now the results look very different. So here I show a subset of models with different initial densities and different initial masses. So you can see that there's still some models that go down to these very low mass loss rates here, and they're also evolving along very small sizes here in the bottom. And those are the models that they basically dynamically ejected all their black holes. And the models that either started somewhat more massive or slightly lower density, they could retain a little bit of their black hole. So the black hole fraction would go down a little bit, but at some point the stellar escape through the Lagrange radii and the stars leaving into the tidal tails would win from the black hole ejections from the core. And the cluster starts almost evolving along lines of constant cluster population mass. So I should have explained this as a function of cluster mass, and so time runs to the right. So here the blue line is our best fit model, which actually it starts with a mass of about 10 times higher than the present day mass, and it reaches this nearly 20 parsec size when it reaches the mass of the cluster. And it currently has a mass loss rate very close or even higher than the Denon models, which started with very, very large sizes. So the initial sizes of the Denon models were way up here, so they were larger than they are today. So these spreads in these, especially the mass loss rate and the size, we show is entirely due to the spread in the black hole fraction at that mass. So, and this is shown in a sort of cross section here. So if you look at when the clusters have the mass of Pal 5, and you plot the number of stars in the tidal tails as a function of the, and the half-light radius as a function of the mass fraction in black holes, you can see there's a very monotonic increase, such that it very much suggests that the size of the cluster and the prominence of the tidal tails are set by how many black holes there are in the cluster. And mind you, they all started with the same amount. So the final fraction depends on how dense the cluster was, how massive it was, and the tides. So, and the best fit model, which is a little bit chi by eye, because we couldn't really in a Bayesian fashion move through parameter space with these embody models. They take about 3 or 4 months to run each, but we had 20 or so models. So the best fit model is shown here compared to the observations. So the density profile is very nicely reproduced. So we only fit here on the size of the cluster and the total number of stars, not on the profile. And of course, the stream is observed, is close to the observed properties because the orbit is pretty well constrained. Plus, Joe's model does a good job in reproducing this. And then on a log scale, I must say the density of the stream and the width are also pretty good, but there are some features in the observed stream that we clearly don't get, and I'm happy to talk about that if people are interested. But now I must admit that we tried also to get a sort of Danon-like model where we start with very fluffy initial conditions without black holes. And we found it was much harder to find that model. So we reproduced the fine-tuning problem a little bit, but we found that it is possible to find an equally good match to the, or at least a similar match to the black hole case. So this is disappointing, but we stick to the fact that the black hole models have a much larger region in parameter space contributing to the error circle of the data. So it's much easier to find a set of initial conditions and less fine-tuning. Plus, there are some collisional features in the black hole models that are not there in the fluffy models. But it's always nicer to put out a prediction, and so we can actually learn a bit more about this. So we looked at what the velocity dispersion of these two clusters were that do an equal good job in producing the density profile. But then the velocity dispersions are very different. So in the black hole case, we expect there to be an elevation of about 50%, which is a lot, but in absolute terms, it's only 200 meters a second. So this is a very challenging observation to do, but nevertheless, we think it's possible, and we're trying now to get time at ESO to get multi-epoch observations to weed out the binaries and find the single star dispersion. There is already data, so Holger Baumgart has a very nice catalog of compilation of line of sight velocities, and the current value of the inner 20 or so stars in this cluster is, sorry, is there a question? No, okay. It agrees very well with this model, but the data has not been properly corrected for binary orbital motion. So at least half of the sample here has only a single observational epoch. So I don't want to yet claim that this is good agreement with between the model and the data. So this needs to be followed up with more systematic search with one instrument and at least 5 or 10 observing epochs to look at the dispersion of single stars. But what's interesting from what we've learned from this PAL5 exercise is that you actually can expect black hole fractions anywhere between 0 and 100%, because near the solution, these clusters could dissolve completely as black hole clusters and leave behind a small nucleus of black holes after all the stars have already escaped. So the goal now is to find out what the frequency actually is of the present day Milky Way global cluster population, and maybe even extragalactic, and try to use that from to constrain models and especially to constrain the initial conditions. And sort of the throwout result as well from PAL5 is that we suggest that many of these streams that have been found with Gaia, and actually Ting Li showed me some very nice results of the S5 survey where they spectroscopically followed up some of these streams. Many of these streams probably have way too many stars in them than can be explained by models without black holes. So we put forward this idea that all these streams that we have been finding with the Gaia satellite and the surveys that are following up, they very well could have been black hole rich extended clusters, which is exciting. So it means we can potentially study now also the properties of black holes by looking at dissolved clusters. And that's a nice topic for future work. So I'll leave you with a quick summary here where I hope I've shown that it appears that black holes of stellar mass are quite ubiquitous in globular clusters. IMBHs, so far it seems at least, most likely not. Tidal streams can maybe even constrain the black hole population of clusters that are no longer there. And we're trying to combine these things to use the properties of globular clusters and the streams to put some constraints on binary black hole production in a dynamical channel. Thank you.
Thanks very much, Mark. I will give you a virtual round of applause. I guess a real round of applause. That was really nice. Okay, so if there's any questions for Mark, you can either hands up in the Zoom or wave at me in the real universe. Okay, Chris, you're up. I think you probably have to be.
Again, this is Chris.
Hi.
So if you add up the merger rate of black holes in all the star clusters of different masses and black hole mass fractions, which part of the mass spectrum dominates that sum?
Yeah, that's a very good question. So one might think that the mass fraction is a very important parameter, but it might actually be the cluster. And I need to say I'm somewhat guessing this now, but I think the rates are higher in a cluster of the same mass and the same density if there are actually fewer black holes. And the reason is that they are more centrally concentrated, so they make tighter binaries. But if you look at just the masses of the clusters, it's the massive clusters that produce more mergers per unit cluster mass. So it scales with mass to the 1.6 or something. So so the massive clusters dominate, and they dominate. It's their early evolution that dominates, right? So not in physical time, but in dynamical time. So it's before they have expanded, because Palomar 5 at the moment doesn't do anything actually. In fact, in the models I looked at the escaping binary black holes because there was no post-Newtonian dynamics in the models, and you only had 1 or 2 black holes that were ejected very early on that could potentially merge within a Hubble time. So yeah, this one is not massive enough to substantially contribute.
Any more questions in the room? I've got it. I've got Shinju. You might want to come up here, I think. Maybe it's worthless running around.
I just have a question. When you try to constrain the stellar streams, have you ever thought about using the power spectrum? I'm wondering, would that be a good indicator for the stellar stream, the power spectrum along the streams?
No, I've seen that people do this. So to look at structure in the streams, you mean?
Yeah, I mean, like just
Yeah,
from the density
I'm not
plot,
sure.
the observation seems to have some more wiggle structure, which I might thought it should be more kind of prominent in the power spectrum.
Yeah, that's probably something that Joe can say much more about than me. But there's indeed there are some features in the. Oh, actually, I had a nice one there. There's some features in the observed stream that we don't get, and I'm quite certain that we miss certain elements that could be responsible for that. So if you look here, so there's an asymmetry between the leading and the trailing arm, which in our models it's not. I mean, this is done in RA, so it's not the best way to look at symmetry. But if you would do this in coordinates that follow the stream, it's very clear that there's an asymmetry. But you can see it also a little bit here. And then these bumps and wiggles in the observed polynomial fits, they are not reproduced. And yeah, there's all kinds of time-dependent features in the Milky Way, of course, that we didn't include, right? So we didn't have a bar in the model that rotates. We didn't have spiral arms that move. We didn't have GMCs, and we didn't have subhalos, substructure in the dark matter. And all of these features have been shown. They could contribute to bumps and wiggles and spurs and all kinds of features that, especially in the GD1 stream, it's full of it. So. Yeah, so yeah, we don't reproduce it, and I think we shouldn't. Whether it would add to look at that, I don't know. We'll learn about the black holes that way. I think you'll learn more about the galaxy that way.
Sure, thanks.
Yeah, I think I kind of follow up about that. You know, is it possible that it's the black holes in the, because I think, you know, the common explanation for the wiggles and things in the density is the like subhalo, dark matter subhalos or stuff like that, right? And people are using the power spectrum to look at that. Like, do the black holes do anything to the stream though? Like, does this? I guess you would see that in this model, right? So I guess not. But it seems like
no, actually
maybe... Sorry, go ahead.
Yeah, I mean, here you can see the comparison between two models, one with black holes and one without, and the data or the embody data lies like right on top of each other. So yeah, it's actually surprisingly close to each other. So and
Yeah, I
these
guess-
models were selected. Yeah, they were selected just to have the correct cluster size and the correct cluster mass at the observed number of stars at the position of power 5. And it turns out then the streams, they just look identical. So the black holes, all they do is they push the stars out if they are not already there. But then when they leave, they don't really interact anymore with the black holes, and there's very little you can say about how and why they left the cluster, basically.
Right. I guess I'm just, yeah, like maybe by eye, I was trying to convince myself that there was more small scale structure in the blue lines than there was in the gray, but maybe you're right. I guess that's
No. what I tried to do, and I gave up. There is some differences. Like, so there's a difference in how the cluster reaches the mass. So the models without black holes, they started with a higher mass, a factor of 2 or 3 higher. So you see a higher stream density if you go further away from the cluster in the models without black holes, basically because they lost more stars early on. But the difference is very small, and when
Right.
you go out to the part, I mean, the difference gets really big if you really move to the other side of the galaxy. So like half an orbit away, the difference is actually really big. The part that we see on the sky are the stars that left in the last 3 GeV or so, and there the cluster evolution is very similar. But if you go 3 GeV further back in time, the differences are really big. But then so many things already can happen on the scale of the Milky Way that can also perturb the stream and dilute the stream that we don't include, that I didn't want to place too much value on those differences.
Right. Yeah.
But
I guess.
yeah,
right.
If you would have a perfect Milky Way model and with all the substructure in it, I would say, well, find the Palomar 5 stream nearby the sun, right, and look at the density of the stream and its velocity dispersion, and then I can tell you whether it is due to black holes or not. But because there's so many ways that the density and the velocity dispersion of the stream can be perturbed after they leave the cluster, I right now I don't think we should do that. Also, we haven't found the Power 5 stream on this side of the galaxy, so.
Right. Yeah. I guess that's a fair point. So yeah,
Yeah.
we need to know the Milky Way a bit better, I guess.
Yeah.
Cool. Okay. Any more questions in the room? Comments? Anything? Okay. I guess I can't see any on Zoom either. If people want to put hands up on there, that's fine. Otherwise, we're just right on time. So I guess we can thank you again, Mark. And
You're welcome.
thank
My
you.
pleasure.